here's what I was thinking for your thing here is, you know, you have what, m x double prime plus b x prime plus k equals, and well, we need a multiplier here. I call it what, a times your Dirac delta of t. So for, you know, given m, b, and k, you're going to get some sort of solution for this in terms of a, and you know, you should be able to come up with that solution. Now you can pick to start with, you know, very much to start with. You can just pick some values for m, b, and k. You know, m mass, you make that 1 kilogram, and so forth, and you could forget about the forcing part, the tapping part, and just solve, you know, for your choice of this thing equals 0 with some x0 equals, you know, how far you've pulled it over. So again, you can just come up with a something there, and actually I think with the pendulum, this x is usually an angle, you know, so it's how many degrees, or well, actually how many radians you've moved it over. You know, but then probably your x prime of 0 equals 0 would be what I'm thinking. You kind of, you know, here it's hanging, and then you pull it over to here, and you just let it go, and so the initial velocity would be 0, but you know, its initial position is probably that angle, I think. And you know, okay, so you could solve that and determine, right, when does this, and I think I said something about right or left, or what, you know, so I'm drawing this where I pulled it to the right, and so maybe you tap it every time it gets back to the right, and so, you know, what happens is this thing swings down here, you know, goes to here, and then swings back. But, you know, if it's damped, then when it gets back to here, it should be lower than x of 0. You know, so it should be here at some time t, and you can figure out, okay, well, when is that time t? You know, what time is that it maxes out? You know, so you're trying to figure out, you know, okay, so you started it, you know, here's t, here's x. You started it at some angle, and it's going to go down like this and come back up, but not quite as far up. And you're trying to figure out, well, where is that? And you should be able to figure out exactly where that is. And so then we'll call that, say, T1 for that first one. Then actually what you want here is Dirac delta of T, well, not T1. Well, yeah, it depends on the notation, but probably you would write it as the Dirac delta of T minus T1. And in essence, right, because if you don't do anything, then this should come down here, come back up, but not quite as high as it was before. And so, you know, and depending, I think I said it one way, and you know, but you can, it's your problem. You can define it how you like, but right now I'm kind of saying, well, okay, so it comes back here. I'm going to tap it right here. I'm going to tap it at this time, T1. Now, how hard do I have to tap it? What's A? So that I actually give it enough force so that it changes this thing so that when it hits its maximum, it's back up at that same level so I can hit it again just as hard. And that will be at some T2. And then, of course, I mean, once I'm doing this, it just repeats because it's the same thing over and over. So the real trick is to find, what is this first time and what's that second time? And, because then my solution will be, it's this A, but it's going to be actually A times Dirac delta of T minus T1 plus A times Dirac delta of T minus T2 plus, and just keep going with that A. Okay, and these are all the times you tap it. And so if you can, for a given M, B, and K, if you can solve this first problem, which certainly you can, and you probably don't want to dampen it too much. And again, you could pick some values for this so that it makes it easier, and just kind of go from there, and then kind of think about, well, okay, you picked particular values. Well, what if you didn't? What if it were just an M, B, and K? Could you redo the analysis then? But it's okay if you decide, okay, I'm going to start with particular values. Well, why? Well, because I know how to do that problem, something like that. But you want something, with these cosine sine curves, and because you want it to, to do that pendulum, but slowly slow down. And so, though, once you solve this, you have a function of t, you can figure out exactly where this t1 is and exactly how tall that is. And it should be shorter than your x0. If it's not, something's very wrong here, because then it's not modeling a damped pendulum. And so then you can start things here at T1. Now, you could also start things over at T equals 0, and do this Dirac delta back here at T equals 0 with the new initial condition. Okay, because again, it's all about where did I end up? What's that height and at what time? Well, if that new height is like x1, well, I could solve my problem starting at 0 with my A up here times Dirac delta of t. But in this case, start with, my x of 0 would equal x1, and get that. So, that's the kind of thing I'm suggesting is kind of just look at that. Can you solve that first pendulum problem? Okay, it comes up to here. Now smack it, which basically sends it up to there real quick. Okay, you want it to send it up to right there. And then it will come down, do the same thing again. You'll smack it, it'll send it up to there. Now, I say that it'll send it up there. That's not really physically what happens, but that's one intuitive way to think about it. Because actually, when you smack it, what that impulse does is actually it adds a little more to the velocity, not the position. But you can kind of think of it like that. A more complicated problem would be, at least I think it'd be more complicated, instead of sort of smacking it that direction, you could smack it up so it did in fact behave like this, but I think that would be a little harder. So you're just trying to get the right constant here on your Dirac delta function so that whatever I start at here at T1 when I get back to the maximum, it will be, because of that impulse function and that magnitude, I'll get back to that height. And so, you know, I think you want to solve this problem with x0 equals something. Again, that's up to you. And then solve that first problem with that Dirac delta and the t minus t1, once you know what t1 is, and in terms of a, right? Because you'll know everything else, so you'll get an answer in terms of a, and just figure out what a has to be to, at your maximum for that next swing, you get up to where you started. And so I think that's what you want to do in a nutshell. And I think, so, you know, sort of intuitively, that's pretty straightforward. I don't know what the calculations are going to be like, but they really shouldn't be too bad, because you can, you know, certainly you can use Sage to help you solve these and check and plot and kind of check to make sure they look okay. And you can, you know, get solutions in Sage, plot them in Desmos, and so forth. The nice thing about Desmos is you can go click on the graph and get values from it and that sort of thing. So, you know, take a look at that, and I think that's the direction you probably want to go. It's reasonably straightforward, and, you know, and heck, we might learn something. So I'll end it there.